Hi to everybody. My name is Enno. This is Daniel.
Hi.
We are going, to talk about attack on backbone technologies, this talk has caused quite some media attention in the, in the last weeks. I'll get back to this later on, but you'll see. I'll just jump into it. My name is Enno. His name is Daniel. We are kind of, long-term network geeks with a special interest in security. We have given quite a number of talks before, and we have already given this one before at ShmooCon, but today it's an evolved version. The talk is split into three major pieces. That is, we are going to talk about BGP, we are going to talk about MPLS. That might be the piece you might be interested in most. And we are going to talk a bit about carrier Ethernet. And in every piece of the talk, there is there are different dimensions. The first dimension is, we want you to reflect on the trust model of the technologies. Here comes kind of the main message of the talk, that is, those technologies use a trust model that might be a bit outdated, and we want to raise, awareness that once this trust model is broken, all sorts of nasty things can happen. Second, those of you who are from corporate worlds and sitting in, corporate security teams might know they're talking about different technologies, and especially the ones that we cover here, usually as a source of grim debates between network people and security people, and debates where all kinds of buzzwords like, oh, this is completely theoretical and nobody has ever done this, stuff you might know from the security bingo. All this stuff comes up. We want you to remind that some pieces of this bingo might apply to some degree, and we want to entertain you. That's why we have included lots of demos. In fact, it's a bit like there hasn't been any talk in the past like this one where I've been so scared about any hardware breaking in advance, as we are completely dependent on the self-walking, as at least 50% will be hopefully interesting and entertaining demos. So this is the bingo I referred to, and during the talk, I assume some, if not most of you, know this stuff. I will pick some pieces of this bingo at different occasions in the talk. But now let's go into it. First piece of the talk is on BGP. BGP stands for Border Gateway Protocol. It's a routing protocol. It's the routing protocol that keeps the internet in the current state alive and running. The most recent version is v4, specified in the RFC 1771. And it's a protocol that is used by, I'd say, 99% of the internet infrastructure to exchange routing information. It has kind of interesting trust model that we'll cover a bit later on, and there have been quite some discussions and security debates on BGP last year. Some of you might know there was a talk at DEF CON that was previously given at PH Neutral in Berlin, but that's a more or less private event, so the heavy media attention came with the DEF CON talk, and those guys showed how BGP can be abused to perform traffic redirection on a large scale. The technical principle of BGP is quite simple. In contrast to other routing protocols, which mainly work above multicasts and hellos and announcing, speakers, with BGP that works over TCP, the entities who speak BGP have to be kind of pre-configured. This is partly due to the fact that it works over TCP, so there is no, multicast-based helloing or throwing messages like, can anybody hear me? I want to join some routing neighborship review. This means on the security side, means it's not that easy to, say, attack BGP as it might be to, say, attack OSPF, which we have done in the past. There has been a talk from us 2 years ago where we released a tool called OSPF Attack Shell. But again, this means it has to be pre-configured, and this means there is some kind of trust in those speakers involved in the BGP conversation. Technically, BGP speakers, which are, once they have formed some kind of adjacency, are called peers. They announce routing information in the sense of, I know that some so-called AS or some prefix can be reached through some AS, and this is called the network layer reachability information. The trust model I refer to is basically the one dating from the 19th or even 80s, like carrier personnel trusts each other, or carrier sysadmins trust other carrier sysadmins, like I configure you or your devices as BGP peers. Once I've done this, you are allowed to kind of speak BGP with me. And usually this is, there might be some extra authentication. There might be some filtering of routes, but filtering is not about trust. Filtering is about control. Those are two different poles. I can trust somebody, or I can control what that somebody does. And I'd say in above 1/3 of the internet, there's no filtering of routes propagated by BGP at all. 1/3 there is kind of some filtering, and in, say, 10 to 20%, there's quite strict filtering about which routes get propagated by BGP. But again, in large parts of the internet, there is no filtering of BGP routes, which leads, which can lead to all sorts of disasters. In the 19th, there was the so-called AS 7007 incident, which brought down in 97 3/4 of the internet. Last year, there was the YouTube Pakistan incident, where where Pakistani authorities wanted to block YouTube. They did so by injecting into BGP, say, more specific route for the YouTube prefixes. Those routes got leaked to the Pakistani upstream provider, which had the effect that large parts of the internet were for some time not able to reach YouTube. And this was 2008. We are not talking about the 90s then. And all this can be kind of credited to the trust model. And once you are member of, say, the BGP speakers, all, again, sorts of nasty things can happen, which is what Alex Pilosov and Anton Capella showed last year at DEF CON. There is some quite widely deployed BGP security control, that is MD5 keys. In fact, it's not built into BGP as a protocol, but BGP uses the MD5 signature mechanism that TCP provides. It's MD5. In this case, there are no large problems arising from the fact that it's MD5. If there were some bells ringing in your heads like, oh, MD5 is broken, be assured it would be very difficult to exploit, say, the MD5 mechanism of BGP in the sense of creating false messages in near to real time. And they work on it. Still, it is debatable, given the trust model, that BGP has to be pre-configured. Once this is done, there is inter-carrier trust. If this MD5 mechanism really adds security value. So far for the, say, theoretical discussion, now to the more entertaining part. after the talk, in fact, the stuff's already available in the web, but we have not yet published the link. After the talk, a number of tools that we wrote, mostly proof of concept stuff, and in fact, it was Daniel who wrote it, so it wasn't me. But all these tools will be available, and this is a kind of set of tools. One could call it, say, like Yersinia for backbone technologies. And the first two tools of that suite of tools is one called BGP command line interface, which was in the initial days just for academic research. We had one guy writing his master thesis about internet trust in BGP. And he needed a tool to kind of simulate how to inject routes, how to prove there is a broken trust model. And that is a BGP command line interface, which we will show in a second. Another one within that set of tools is a tool we developed to crack BGP MD5 keys. The main intent behind these tools, again, is proof of concept to show that the trust model is broken. It's not, I mean, obviously, I won't advise you to use those tools in practice, in carrier backbones. And I want to make clear the use of all the tools that we will release today requires somehow access to a backbone network. I won't discuss how to get this access. I will get back to this discussion a little later on. But given the media attention of this talk in advance of Blackhat, I'm a bit tired of explaining the message of the talk, which I want to make clear again. It's about trust models. It's about technologies with outdated trust models. We will not cover how to get into carrier networks. We assume an attacker has gotten access to a carrier network. So we cover one part in a staged attack. There is, again, I said I'm a bit tired of this. There's a large debate, like carriers will tell you, oh, all this, what those guys do is completely, not that theoretical as we release tools, but it's out of real life scope as we protect our networks and don't let anybody in. That's a legitimate position, and we won't discuss on this, but be assured, both of us have been working in carrier space for a long time, both mandated by carriers, with mandated security assessments, both on the customer side, performing data center visits and stuff. We would not completely rule out the possibility somebody gets into a carrier network, either physically or logically, but this will not be covered in our talk. We assume attacker has access. So what can an attacker do with those tools once he has access? We'll give some demos here. Unfortunately, we have a monitor switch that doesn't work with the other piece here, so we have to switch manually. Okay. Where's this micro? Where's the other mic? Thank you. Oh, I was wondering.
Okay, so first I will show what one can do with the BGP command line interface. So I will just launch it up, and once we got that interface, we can create a BGP session which needs some argument, which is our AS number. In this case, it's just the AS2, and we need to define some timeout value, which I choose really low to just for demo purposes, that we don't have to wait such a long timeout. Okay, once I've created a session, I can connect to my BGP speaking peer. So the tool establishes a BGP connection, sends out BGP hellos, and starts and keep a live thread in the background just to hold the BGP session open and our routes on the router. Okay, so once we got an BGP session set it up, we need to create our BGP update statement, which looks a bit ugly, but this is because you can set such a whole bunch of stuff in the BGP protocol. And if you create your update message, you can just send it out to the peer, and after that, Anno will show you what's happening on the other side.
Sorry for having to switch, but hopefully you will be able to follow our stream of thoughts here. What you can see here is the routing table of the device that is affected in this case before Daniel performed his actions. Here you might see, can everybody see this? We noticed that, I'll put it to the top of the, can you see it now a bit better for everybody in the back? We noticed that sitting in the back, one can't see everything that's going on here, but thankfully we are, the ERNW slides have this piece, so the stuff is in the upper half of the slides anyway. So this is the routing table. Before, say, Daniel put anything into effect, here one can see that a new neighbor came up that he established manually. No router needed, nothing, say, fully fledged BGP stack needed, just a command line tool. And now I'll have, again, a look at the routing table. And you might notice there is a new route showing up here that hasn't been in the table before. And that is exactly the route that Daniel injected. So far for the first part, I suggest going to the second immediately, which shows the next tool. Again, I may remind you there is some security control built into BGP, that's MD5 keys. Those MD5 keys secure the authenticity of the peers and the integrity of the transmitted packets. So it is assumed both sides know the right key, and once they know the right key, only then they will be able to perform, say, a valid BGP interaction. Do names. Let's now assume we are connected to a router that has MD5 authentication and integrity checking, but the MD5 key enabled.
So, okay, I'm now another configured peer, and once I brought my IP address up, the other side will just start polling me, not this one, but okay, so the other side will just try to SYN me, and my peer won't answer with the right MD5 key, so it pops up a message on the router side which says, okay, there is not the right key configured.
Soll ich mal kurz sagen?
Yeah.
Okay, what we see now, I mean, we have, this talk was initially composed for 60 minutes, so we have an extra 15 minutes, which adds the capability to explain all demos a bit more in length. Now let's assume what you see here is a given router. The attacker sits, say, on the other side, but the attacker does not know the MD5, the correct MD5 key, which shows up in TCP bad auth messages, clearly indicating, okay, somebody tries to establish a BGP connection with us, but that peer does not dispose of the right key. How can we, or how could an attacker solve this?
Okay, this is one of the packages sent out by the router. He will just SYN me and try to establish a BGP connection with myself.
Can everybody see this from the back? Is that big enough? Okay, thanks.
And even this first package, which is just a TCP SYN, carries an TCP MD5 signature, which indeed is on the bottom of the screen. I will try to lift it up. Okay, so here it is. It carries the TCP MD5 signature, and once I've sniffed such a packet, I can easily launch the tool on this.
So there isn't even a successful connection needed. It's just needed the other side tries to establish one that is secured with the MD5 key. And if I sniffed such a package, which I got in this demo pcap file, I can run an 800 brute force attack or a word list attack against this key. And you see after 7 seconds, I've tried about 4 million keys. So I choose a 20 megabyte word list just to show how fast MD5 can be broken. But you see, I easily get out the key, which is secret in this case. And once I got the key, I can launch up the BGP command line again and just set the MD5 key for my peer, which is secret in this case. And after that, I can establish a connection, build up my update statement, and send out the update to the other side. And again, I will have received this, what I show in a second. I mean, the interesting part is not only about receiving it, the interesting stuff is already here, that the neighbor comes up. So there is a neighbor that has not disposed of the MD5 key in advance, but has managed to get a packet sent from myself, to crack that packet with a tool. You might have noted again, 4 million tries in 7 seconds on a laptop. That's quite fast. The same stuff could be performed. The BGP command line interface can perform, say, brute forcing the key, but that is very slow, and it will show up in messages on the router side. This will not show up at any point on the, say, attacked router, as it is a passive attack with a packet taken from the wire and the key extracted, and after that the connection will be established. Most probably, again, I'll see some injected routes here, but again, the most interesting piece is already, shows up here as the neighbor comes up, which had no knowledge of the MD5 key before. So far for BGP. BGP, we will kind of meet BGP again during this talk. The first part of the talk is covered. We will, for completeness sake, just to make you aware of the BGP keys used in the wild, some time ago we performed a BGP and MPLS audit of a 40K user environment, and this is the BGP key they used. And funnily enough, that BGP key was derived from, say, how to set up MPLS in customer environments guide from one of the world's largest network consultancy corporations. So we can safely assume the technicians on site just performed the commands that were described in that guide, and we might assume that they performed the same commands in other environments as well. But yeah, this should be sufficient for BGP. Let's switch over to the second technology covered, that is MPLS. MPLS stands for multi-protocol label switching. The most important RFC is the one 3031. And simplified, explained in a simplified way, it's a technology used for forwarding packets with means of labels. So small entities of 32 bits are attached to packets, and based on these entities, which are called the labels, subsequent forwarding decisions will be done. This can be used to accelerate traffic flows in carrier backbones. This can be used to optimize bandwidth use. This can be used to segregate different customers' traffic, as we will see. But so far it's sufficient to know it's about forwarding packets with simple entities that are attached to the packets. And within the, say, MPLS technology and protocol space, there is one technology that has gained some acceptance and say as a service for corporate networks, that is so-called MPLS VPNs. This is just a subset of technologies. This is not the whole MPLS space, but it's a quite important one. And we can safely assume that most large networks, most large organizations that work or act globally use to some degree MPLS VPNs, which they don't build themselves, but they get as a service from the carriers. Those so-called MPLS VPNs, sometimes they are called MPLS layer 3 VPNs, are say subset technology specified with in the RFC 364 with a known concept and a known terminology. It's about say using a shared infrastructure, the carrier's infrastructure, for separated routing of separated customers' traffic. And here those labels come into play to separate the different customers' traffic. That's the exact role within this technology. To understand the following, it might be helpful to have an idea of the terminology. In the MPLS VPN space, usually there is, say, the provider or carrier network called the P network. There are customer networks called the C networks, obviously. And the routers connecting one, say, area to another one are called the CE routers on the customer side and the PE routers on the carrier side. And within those PE routers, one can usually find a bunch of routing tables called VRFs, virtual routing and forwarding instances, for different purposes and different customers. So part of the concept is that there is not only one global routing table on the PE devices, but there are different small, or so more or less small, routing tables for different customers in separated kind of logical spaces. So we have a global routing table, and we have those so-called VRFs. Essentially, a bit more from a technical perspective. What we have then is, let's imagine we have two customers here, a yellow one and a green one, and those customers dispose to some degree of the same address space. And what happens then is that for each customer, there is a different VRF on these PE devices connecting to customer-specific CE devices. And those PE devices, which are part of the carrier backbone, they belong to the carrier. Usually they belong to the carrier. I am often consulting to network teams or security teams of large organizations, and I sometimes accompany them to, say, data center visits or to meetings with the carriers. And I'm known for making fun of the situation by asking the carriers something like, oh, listen, if we signed the contract with you, and usually that's about contracts in some million for some years, dollars or euros range. If we signed the contract with you, we would like to run our own PE. Is that possible? And I'd estimate 1/3 of them, of the carriers we face in the situation when I'm on the customer side, immediately denies. They say, no, this is not possible, 1/3. One notable example might be BT here in Amsterdam. I had the exact some meeting like that here in Amsterdam and ask, oh, we would like for security reasons to run our own PE. Would that work? No. Yeah, but then if we paid, no. They denied it immediately, but that is 1/3. Another third is like, oh, well, why do you want to do that? We will have to check. And the last third is, yeah, we might be able to do that. So think about this when talking about carrier trust and carrier security. If the carrier allows to bring some other organization to bring PEs that take part in the backbone in, that might somehow invalidate the trust model, wouldn't it? Okay, but back to the technical specifics. Those PEs have different routing tables now belonging to different customers. What happens next is that they advertise or propagate by means of a, say, modified or enhanced version of BGP called multi-protocol BGP. By means of multi-protocol BGP, those PEs propagate to the other PEs information like, if you want, imagine this one. This one tells this one, dear colleague, dear peer, if you want to reach this prefix, if you want to reach the network 10.2.00 in the green customers VPN, please attach some label with a given number. Those labels can be thought of like simple numbers. Please attach the label with number, say, 25 to it. So this one has the information. If I want to reach this network in the green VPN, I have to send my traffic into this direction and label it with number 20. So this one can recognize, okay, this traffic belongs here. Same might go like, okay, if I want to reach 11.600 in the yellow VPN, I have to send it to this one, and I have to label it with the label 137, for example. So in short, the labels are responsible for kind of the whole VPN thing in the sense that the traffic separation is based on the labels. Remember, labels are for traffic forwarding, taking traffic forwarding decisions based on labels. This is exactly what happens here. Which brings us to the, say, exact problem. What happens if those labels got somehow modified? The trust model of MPLS is that a trusted core is assumed. It is assumed that this whole space is secure. There is no built-in security of MPLS whatsoever. There is no integrity checks. There is no authenticity control of the peers. There is kind of nothing. In MPLS and MPLS VPNs rely on the fact or on the assumption that the underlying network is secure. Once this assumption might somehow be, say, taken into doubt, then one has all kinds of problems might show up. And this exact, say, assumption is the source of grim debates between the network teams telling the security teams, oh, yeah, we know that MPLS might be vulnerable, but nobody has ever done this. and you're paranoid. This is exactly what security people in large organizations are facing once they bring up the question, oh, MPLS, is this secure? Are the carriers secure? That is the usual answer from the network people's side. So again, it's time for some demo, it's time for some tools. The first tool that we are going to show is called MPLS redirect. It assumes that the attacker has access to the traffic path. Again, I want to make clear, this talk is not about how to get into a carrier network, but what to perform once you are into. It's a command line tool. It modifies VPN labels of packets flowing through the network. So essentially, it gives an attacker the ability to redirect traffic from one, say, customer to another customer on a large scale, sitting in a backbone. Again, we have prepared a demo. This demo works essentially like this. Let's assume there are two customers, a red one and a green one. Given this talk is in Amsterdam, we chose the names Spear and Spliff, which might play a role later on, but red and green would be sufficient as well. So we have a red VPN, we have a green VPN, both VPNs for the purpose of this demo. You will see later on this is not too important. In some attack scenarios, they have the same address space, but let's assume they have the same address space. And what we will see now is, in the first step, I will show that, say, an entity sitting in the red network can successfully, and this is somehow expected behavior, can successfully ping another entity in the red network. I will, for the purpose of the demo, I will perform this right from one of the devices to save. We have some cables here and 3 devices. We didn't want to bring any more, so we perform some stuff sitting on the devices on the PEs. But the same, it does work the same way if there was a physical CE attached. The origin of the ping will be this device, but I'll modify the ping in the way that it is only valid within one VRF. So it's kind of it's stuck to the red customer's network. The other side, the recipient of the ping, is my simple laptop. So I have an address here that is 182.168.113.2, and I will ping exactly that one within a given VRF, and I should be able to reach it, which is the case. You might note I kind of put the ping into this network and into this routing table. So this ping is only valid, or the say traffic forwarding decision is based within this space of the red network. What I will do now is that I will physically, move to the green network. So this laptop is no more located in this space, but now is sitting here. Obviously, this means this ping shouldn't work anymore. It might work if I performed it in the green network. as now I'm sitting in the green network. And here it works. This means now the traffic recipient is sitting in this network. I just noticed this is a bit in the bottom of the page. Hopefully everybody in the back can see or understand what we are showing. But it does not work in the red network anymore. I mean, there is the box is physically unplugged. But imagine a box would still be there. This essentially means the traffic separation works at the very moment. Red entities can ping to red entities, green entities can ping to green entities. But red entities cannot ping to green entities. Now I'm connected here, and the red entity is not able to reach me. I mean, again, referring to Amsterdam, mixing beer and spliff might cause a state of unresponsiveness, and this is exactly what happens here. So now let's add some magic into the play. There might be some resolution to that state of unresponsiveness caused by mixing up beer and spliff. We might add some more stuff, what we call magic here. And this magic will help to enable the red entities to reach the green ones. We will show the tool before. But before I dig into it, to give you an idea of those labels. We can show that different labels are used for different traffic. It's like here is a label 19 with number 19 and label number 17, and we have a 20 and an 18, and those belong to different customer entities, customer networks, customer routing tables. We have the red one, we have the green one, and even though the exact similar networks are present, the traffic separation is done based on the labels. So one PE sending packets to another PE, which are labeled differently, will have different forwarding decisions on the other side. Like, okay, this packet arrives with a label 20, put it into the red VPN. This packet arrives with a label, say, 19, put it into the other VPN. So what happens now if some tool comes into play?
So, okay, I will launch up the little magic tool, which is called MPLS redirect. So I just gave some input and some output interface for the sniffing and injection stuff, and say, okay, just label all incoming traffic with label 17 to outgoing label 18. So this is the traffic in one direction, and on the other side, I'll launch up a second instance of this tool, which just does the same for the backward traffic and says, okay, label all incoming traffic with label 20 to outgoing traffic with label 19. So that's all the magic stuff.
You might notice we use a bridge interface here, which might bring up, say, a carrier's response. Yeah, but we don't let people with Linux boxes with bridge interfaces join our networks. This is just for demonstration purposes, again, to show that traffic relabeling is, once the attacker is in the right position, might be easy.
Yeah, you could do this with some ARP spoofing too.
Yeah, we will see more stuff. The point is, I mean, Cisco is moving with some of the platforms, is moving to a Linux base, say, operating space in some sense. There have been FX talks on shellcode, on iOS and stuff. We leave it up to you if we regard this feasible or not. Our intent is just, let's assume somebody got into network, has compromised the box, what will happen next? And yeah, the impact of those tools running is that now, remember that I'm still, you might have noted, I did not touch anything over there. I'm still physically located in the green network, but trying to reach me over the red network gives a response. So what happens in the backbone is now the traffic in both directions is automatically relabeled, and all the traffic flowing from red to red at some point gets kind of diverted, gets kind of forked to the green network, and in the green network sits an entity that replies, and the response traffic gets redirected as well. So this would essentially enable traffic redirection on a large scale, and this would be go completely unnoticed. Again, there is no checksums, there is no way kind of detecting this is going on. All the traffic destined for this side will flow to this side as well, both directions, and nobody will be able, most probably not even the carriers. I mean, they might be able, there is some compromised entity in our network, but given the traffic flows, monitoring the traffic flows, this will be completely undetectable. So now, this is what we just showed. We have a successful, say, VPN hopping in the backbone. But yeah, what does it mean? I mean, this might enable an attacker to set up, say, a fake central authorization portal, redirect traffic to it, respond to the traffic, grab all corporate logins into this. This would be the same for DNS or LDAP, whatever. Still, one could argue, like, yeah, nice demo you showed. Oh, by the way, I think this was a nice demo. So you could, huh? But we have an even better one. I mean, it's about relabeling existing traffic. And we somehow assume, okay, there is the same address space used in both, say, customer networks. Wouldn't it be nice to have a tool to inject various kinds of traffic into some given VPN? And this is exactly what the next tool does. So we have more meat here, which is called MPLS TUN, obviously for MPLS tunnel. Again, this assumes an attacker has access to the core. It creates a virtual interface that is part of a given MPLS VPN. And once an attacker has that kind of, say, VPN-enabled network stack, an attacker can use all kinds of tools to inject traffic. Think of it like a packet mangling machine that adds labels to given network traffic. So we don't have to rely on the fact there is traffic coming along that has to be redirected, but we establish a kind of virtual connection with any given VPN, assuming, again, we sit in the backbone. We have a demo. What we will do during that demo is quite simple. We will perform an Nmap scan. I think we have to go to the... Just give me the... Did you modify? No, this one. Let's assume we don't want to redirect or support existing traffic, but to inject labeled traffic.
So, okay, so launch up another tool, which is MPLS TUN. It just opens layer 3 tunnel adapter and listening for incoming and outgoing traffic on, again, the bridge 0 interface, and accept all incoming traffic with label 19 and labels all outgoing traffic with the label 17. So as MPLS is directly based on layer 2, we have to define both MAC addresses, one for the destination host and one for the source host, which is a configured MPLS speaking device in the backbone network, which we're just replacing. Remember, we're sitting in the traffic path, so we see traffic flowing from one provider device to another one. So we have to define both MAC addresses as well.
And we assume both are based on Ethernet in this case, as we added the MAC addresses, but I mean, there is a shift towards Ethernet anyway, but this obviously would work in other contexts as well. Again, it's just mainly for proof of concept.
Okay, so once I launched up the tool, there is a new interface coming up, which is the Tunnel 0, virtual tunnel interface. And once this interface came up, I can just set an IP address to this interface. As we are labeling the traffic, we just lose some part of the MTU, so I'm setting a smaller MTU manually, and after that I'm adding another route to my routing table for the destination network. You remember it was the 113 network, which is Anno's laptop sitting in, and after I did all these steps, you see I got a virtual tunnel interface with the given IP address, and I got a route to the destination network, which is just the customer network on the other side.
So every traffic created subsequently on his laptop will be labeled automatically, so it can be injected into that into some VPN.
Okay, so just to prove it, after establishing the tunnel and setting the IP address and adding the route, I can easily ping Anno's laptop inside the customer's VPN.
But I mean, pinging is, might be a bit lame. We already saw we can ping somehow. More interesting stuff might be added.
What's about using your favorite scanning tool right out of the backbone and scanning devices inside the customer's VPN?
Obviously, you see it's a Windows-based laptop with some strange ports opened. But this should give you an idea that it is quite easy with this tool to inject any kind of traffic into any given VPN. So far no, we don't see my laptop. That's the second. That was the second piece of the talk, discussing MPLS and the underlying or inherent vulnerabilities of MPLS and the, say, problematic trust model. All these tools, again, will be available after the talk. What about, say, mitigating controls? This is a question that immediately comes up. Okay, guys, what can I do about this? Problem is, this stuff is, there is no vulnerabilities on the code base. Those are, say, weaknesses in the way those technologies have been developed and are deployed. Nowadays, I mean, there are research circles discussing, say, stuff like next generation internet. In those circles, nobody would, say, implement network technologies anymore without, say, peer authentication or integrity checking or whatever. But these technologies have nothing of that. So you are essentially stuck in a position like trust your carrier, which is okay. We don't. It's not about mistrusting your carrier. It's just about risk management. Understand, okay, if this assumption of trust is broken, as I'm running a global network and I have data centers in, say, Asia Pac, and those carriers' data centers and carrier hotels might be located somewhere in, I won't name any cities in Asia Pac where you might assume that physical security, or especially physical security against state authorities, might not be given. But, okay, you can trust your carrier. That's okay. If you don't, or you might try to bring in contractual controls like, say, SLAs for integrity. Ask your carrier something like, okay, we have an SLA for availability. Would you mind, once you tell us your network is absolutely secure and nobody will ever be able to perform stuff like this, would you mind signing an SLA for integrity? You will see interesting reactions then. But there are carriers who move towards that direction. Again, BT might be an example. With those, we have negotiated stuff like that in the past. Okay, one might say, okay, I have to authenticate. I can't trust the integrity or authenticity of traffic flowing across the backbone. I have to authenticate everything. I mean, that could be done, but that would be not kind of very efficient. Same stuff. Implement borders of trust between your networks and the carrier's network with encryption. But then you might have the discussion with the network people. Oh, we took MPLS and VPN to get rid of IPsec boxes everywhere. Didn't you tell us we could save a lot of money then? Yeah, I mean, it's all about risk management. Understand what can happen, rate it for yourselves, take the right decisions and directions, but understand this stuff is real stuff. It's not theoretical stuff, at least not after today. Okay, third part of the talk, Carrier Ethernet. Carrier Ethernet basically is a set of technologies where Ethernet frames are transported across a carrier's network. It's not about connecting by means of Ethernet, or which is called in carrier lingo Ethernet as an access. It's about transporting Ethernet frames coming in on one side across the backbone, getting out on the other side. And the summary term for this is carrier Ethernet. The underlying technologies might be MPLS, and there is a flavor that is in Cisco space called Ethernet over MPLS. There is something called VPLS, Virtual Private LAN Service, which is a multi-point Ethernet MPLS stuff. There is so-called Metro Ethernet, which is a completely different technologies, and some carriers, namely Sprint, for example, use L2TP, another protocol for this. The basic principle, again, is Ethernet in here, Ethernet out here, which might be interesting for some applications and some scenarios. SAN replication is one space where this is more and more asked for. Again, being on the theoretical side, interesting about this is that it changes the whole trust model of Ethernet. The trust model of Ethernet so far has been like the border, say a layer 3 device to a carrier was a natural border of the zone of trust. So let's say somebody responsible for security inside A never had to take care of security vulnerabilities of Ethernet inside B, as they couldn't cross, say, the carrier network. Now one has some large zone of trust. Those Ethernets might be able to be visible, to see each other, and we even have a third party in between our large-scale worldwide Ethernet. This has large implications in the security space. This might have implications on existing attacks. It might be possible to, say, upspoof, to perform all kinds of layer 2 attacks from one side against another side. We tested this in a Juniper test bed, and it worked like a charm. We could upspoof devices, hosts on one side from the other side. Misconfigurations will have larger impact. Stuff that goes wrong Ethernet-wise in one side will affect other sides. And new threats may show up. New threats may show up as the current Ethernet protocol space was not built for constructs like this. It dates, some protocols date back to the 80s. And the segmentation capabilities might not be appropriate for some security needs. The segmentation capabilities in the backbone are either MPLS labels, and we have seen those might be vulnerable to some degree, or those are VLAN tags, and I mean both MPLS labels and VLAN tags are small entities sitting in a header. There's no checksum for them, so they might be easily be modified. So yeah, this would be the attack. Attacker performing actions from one physical site against another one, with, in this case, with Yersinia, a layer 2 attack tool. Some or most of you might know. The attacks might not be only performed over the cloud, like here, but remember our tool, MPLS tunnel, they might be performed from within the cloud. An attacker, having compromised somehow by some magic that carriers regard completely impossible, somehow compromise the box, running up stuff like MPLS TUN would enable the attacker to inject any kind of traffic into a given VPN, be it layer 2, be it layer 3. An attacker might be able to inject ARP frames, effectively forcing traffic that was thought of to stay within one site, to force that traffic out of that site. So we're thinking like, okay, all the sensitive stuff happens within the site, never leaves the site, goes to the carrier cloud. This might be short-sighted, as the attacker might be able from the backbone to force traffic get out by, say, injecting falsified ARP frames. We have coded, or Daniel has coded, another tool that is called LDP, Command Line Interface. LDP is Label Discovery Protocol. That is a signaling protocol for MPLS as a whole, but it has another meaning in layer 2 VPNs, in layer 2 networks built with the help of MPLS. We won't show this. We just mention in our tool suite to be published in 10 minutes. There will be another one like BGP command line interface that enables security testers to build, say, manual LDP associations. To wrap up carrier Ethernet, this is an interesting approach. From the networker side, we find this pretty exciting. It's gaining ground commercially. For example, for SAN replication across the cloud. It changes the whole trust model of Ethernet. So keep this in mind once in your environment, stuff like this might be on the desk. We are pretty much finished. We have one last thing, last demo before we finish. This is a demo of the space like an attack that has mostly been regarded theoretical in the past. When we brought this up, or when other people brought this up, it was like, yeah, nobody will ever do this. It's too complicated. Somebody has to get access to the core and to read the labels and to modify multi-protocol BGP and stuff. So we think it's a nice one. Remember, multi-protocol BGP is the protocol that is used for signaling between the PEs, like, dear colleague, if you want to reach this prefix in the, say, yellow VPN, you should label the traffic with number 20 or 25 or whatever. This information is propagated by multi-protocol BGP. What happens if an attacker can modify this information? An attacker might be able to inject, say, additional sites into a given VPN, to add new routing information to the VRFs. So the attacker might not be, it might not be needed to modify the subsequent traffic on the fly, but modify routing in advance, like all the traffic getting into the backbone destined for the site over there. There is a more specific route which routes some kind of traffic, say for the corporate DNS server, just over there. And this can be done with our tool again, in which VRF are you injecting?
Red.
Okay, let's have a look at the routing table of some given VRF. The routing table looks like this, not too many entries at the very moment. Now Daniel will fire up a bit strange command line.
Okay, so I'll use the BGP CLI again. First of all, I have to set my BGP capabilities, which just tells the router in the hello process that I'm capable of multi-protocol BGP and that I'm capable of some kind of route refresh and stuff like that. That's necessary for getting into the multi-protocol BGP connection stuff. Okay. The next thing is just to set up my session again, connect to the peer, which is done now. I got a keep alive thread and all my updates are accepted. Once this state is arrived, I build up my BGP update statement, which is an BGP multi-protocol update statement. It looks really ugly. But
yeah, this is the command line I was referring to.
Okay, but maybe you can see injecting a host route to this host, and I'm just telling, hey, label every packet to this host just with the label 120. Okay, so after build up my BGP update statement, I can send out this update, and after that,
ideally, we will have a new route in the VRF's routing table. You might notice a new neighbor came up in the meantime, and if I look at the routing table now, there is a new route in it. Effectively, given this is a 32-bit route, effectively forcing all the traffic flowing towards this host to flow into some completely different direction now. Yeah, that's what we think is quite smart. Okay, so summary and outlook. Our talk was mainly, besides showing some nice demos and some what we think nice tools, was about trust models of backbone technologies. We want to raise your awareness. These technologies have trust models that are outdated, that might be debatable. You should know that. You should know that attacks that have previously regarded completely theoretical have moved into the practical space, and that was the main intent of the talk. All the code will be available at this URL from now on. I leave it up to your imagination what this string might mean. Thank you for your time.